All right, so I want to talk a little bit about signaling between processes. I got to this in the afternoon section yesterday, but not in here yet. We've talked about processes, right, and forks and exec and all that kind of stuff, and we know that we can use the PS command and see what processes are running on our system. And if I say something like sleep 1,000 seconds, right, that command is running, and generally what I type here is being ignored because the shell's not listening to my standard in, the sleep command is, right? If I do Control Z, that suspends a process, and if I do my PS, you can see the sleep command in the middle. If I do BG, that says go ahead and keep running this process, but run it in the background, so now the shell is listening to my standard in, but the sleep command is still running, and so it's counting off 1,000 seconds silently. So I can come into a totally separate window, right, separate bash process. And I can do the following. So this sleep command has a process ID of 18478. So I can say kill 18478. And over here, my sleep process has been terminated. So do you know the yes command? If you say yes, it just prints out Y forever. And if you say yes, hello, it prints out hello forever. Yes, no, prints out no forever. So let's just run yes, haha.
Like a loop?
It's just a big loop. So that's process 18514. So if I kill that, right, it terminates that process. So we can send signals from one process to another using this kill command. What is a signal? It's not always something that causes a program to exit. Okay, it's really just a message. And there's a variety of messages that we can send. Basically all of these things. So sig prof and sig winch and sig IO and sig quit and sig int and sig hang up and all of these. These are different messages we can send to a process. Now, the majority of these cause a process to terminate. But for most of these, we can control what happens when we get one of these signals. And there's a couple of signals. Where are they? Sig user 1 and sig user 2, which are sort of user definable. They don't have a particular purpose, but we can use them to do rudimentary communication. So what is signaling? Signaling is like, hey, over there, right? Get something's attention. That's basically all you're doing with this. Now we can't send a lot of information. We could send a different type of signal, but there's only a few dozen signals to choose from. But we can get a process's attention. And typically what we might do is create a pipeline, okay, and then fork and have the clone turn into some other process. And now we have a process running, but it's got access to one end of a pipe that we have control to the other end of. And if we want to send a message to this process, we could do the following. We could shove a message into the pipe, and then we could send a signal. And the understanding would be on this other process, when it gets the signal, it should read from the pipe and try to figure out why we signaled it. And the pipe might contain some sort of coded message that says, okay, read some more information from the pipe, or take some action, or terminate, or whatever. But unless this process is going to continually be checking the pipe, right, we need a way to tell it, hey, there's some information for you, and so typically we could use a signal for that. But if we don't do something in particular, most of these things just terminate. 15, 18, 5, 34. So So there's a sig user 1, and my process printed out the message user defined signal 1, and then it terminated. Why is there this yes command, by the way?
To test signals?
Well, that's a good use today. So a lot of times when you run particularly administrative processes, you're trying to install some software, and typically it asks you lots of questions along the way, like, this will update your software, do you want to continue? And you say yes. This is going to write into this file, do you want to continue? Yes. And you end up saying yes like billions of times. So you just say yes, and you pipe that into your update command, and it automatically says yes every time it asks a question.
There are so many times I could use that.
Yeah. Right, and it's an easy program to write, right? It's just a little loop. It's probably like 10 lines of C code, and if you give it an argument, it just prints that out instead of Y. So if you're being contrarian, you could say yes, N, and pipe that in, and it'll always say no to your requests. Or if you want to remove every file unless it's like protected, you could do an RM, -R in any file that's protected, but that you have permission to remove anyway. It'll say, do you want to remove this protected file? And it would automatically take it as a no. So that's a kind of useful command. All right, so for programs that we run from the command line, right, we can use this kill command, right, to send a signal. And that's great for bash and bash type things, and we looked at the trap instruction, I think, in bash to catch these signals. But we can do this from a C program also. And we need a pair of functions to do that. And the first is, not surprisingly, called signal. And the second, even less surprisingly, is called kill. So if we look at signal from chapter 2 of the manual pages, it's a callable function. And it takes two arguments. It takes a signal number, right? These signals are identified by integers. And it takes something called a handler. A handler is basically a function. And so what we can do is we can say, when we get this particular signal, I want you to make a call to this function. And this can be a function that we've written, and we specify it up here as a second argument, and then once this process is running, anytime it receives this signal, it'll call this code. And this code will execute, and when this code returns, the program will continue wherever it was when it got the signal. So here's some sample code. So I'm prototyping handlers as something that takes an integer. So our main program starts, it makes a call to signal. The signal that we're going to trap is sig user 1. And when it receives a sig user 1, I wanted to call this function called handler. Right? I could call it anything that I want. And signal itself can return an error message. So I check to see if it returns an error, and if it does, I'll just print a message and exit, but that's not going to happen. So we do this one-time setup, right? We make a call to signal, and then we enter the main loop of our program, which is just an infinite loop. So while forever, we sleep for 1 second, we print out the message waiting, and I'm just doing an flush to flush the output buffer. So we actually see the word waiting. So this is just going to sit here and it's just going to loop, right? It's going to run forever. And it's just going to print out the word waiting every second. Okay, but we set up a signal handler here in the beginning to trap sig user 1 and call this function handler. So let's look at handler. That's this code down here. So what does it do? Well, handler is called, it's given a signal number. That's the signal that caused this to be called. So I check that to see if it's equal to sig user 1, and if it is, I print out the message ping, I sleep 2 seconds, I print out the message pong, and then I return. And if I get called with some other signal, I'll just print out the signal, but that's not going to happen. So what does this remind you of from Engineering 270?
The delay.
the delay, what about it? That's the right area. Your program's running and then something happens and all of a sudden we're executing this code and at the end we return back to where we were. Is that familiar?
I would say that's a statement.
Interrupts.
It's an interrupt, yeah, it's got ifs, but it's an interrupt. Right, so we set up all these registers, intcon, all this kind of stuff, and then we went into a loop or did something, but when some event occurred, all of a sudden, we made a call to memory location 8 or 18, started doing some stuff. When we got to a ret fee, we went back to where we were when that external event happened. It's exactly the same thing here, okay? This is a software interrupt. The event is something issuing a kill, right? Sending a signal to this process, and when it receives that signal, it pauses, comes down to this handler, it does this stuff. When it says return, it goes back to where it was. So let's make this a little more interesting. Bless you. So let's just print out consecutive integers while we're waiting. I guess I should recompile. All right, so this is hanging out, it's doing its thing, it's sleeping, it's printing consecutive integers. And this is process 18639. So I can send a kill message to that process with a signal sig user 1, and our process jumps out, it does ping, it does pong, it comes back, and it continues right where it was. Alright, so we just did a software interrupt. So I can do a bunch of these kills, and it looks like it only noticed 2 of them.
So the ping pong does mean the interrupt.
Ping pong means it's inside an interrupt routine. But here's what happened. We sent that first signal, okay, line 2005 up the top there. We sent that first signal, it generated an interrupt. It hopped down into our handler, it printed out ping. And while it was sleeping in there, we sent it a second signal. And that basically generated an interrupt request. It said, hey, I want to interrupt you. I got a signal for you, right? And then we sent a bunch of other kills. And each of those basically said, hey, you got an interrupt request. We want to send a signal to you, right? But those don't queue up, right? Just like if you try to generate an interrupt and you hit the interrupt pin 1,000,000 times, you get one interrupt, okay? So we got one interrupt that brought us into our first ping, and then all these other ones basically did the same thing. They just said, hey, we're sending you a signal. It's not going to respond to that signal while it's inside the handler, but as soon as it came out of the handler, it said, oh, I got a signal coming. It went back in, did ping pong, came back out, and that was it, right? So it's really, really, really close to an analog of a hardware interrupt. It's just a software one. Now, if I kill it with some other signal, like sig user 2, it tells me it got user defined signal 2 and it terminates, right? Because I'm not trapping that.
So the number 18639 really matter. It's really that.
So that I got from here, right? So I did a PS to see what processes were owned by Nick, and I looked for one that had the word signal in it, and that was 18639. Now if I run this again and I try to send this signal, it says there's no such process 18639. because now the process is 18674. Right, so each process has a unique ID, and when you send a signal to a process, you use that PID to get its attention. So I send a SIGINT, that just interrupts it. So we can set up a handler to trap a SIGINT instead of, and we can trap a SIGINT. So now if I kill process 18687 with a SIGINT, tells me it got signal 2, and it goes back to waiting. And when I hit Control C, guess what? It's ignoring me. Well, it's not ignoring me. Control C sends a signal to the process that's in the foreground. And since I'm trapping SIGINT, which is generated by Control C, it says, oh, I got a signal 2, and it goes back to where it was. So I've made a program that can't be Control C'd. Could be useful. So how can you stop it?
The X in the corner?
Is there a hard kill?
So just a plain kill will kill it. And yes, there is a hard kill. So I don't know what the default kill is. I think the default kill might be sig term. So let's try this. Alright, so there's a signal, we can't Control C it. And if we try to kill it, 18712. Alright, so that's a sig term, signal 15, and we're trapping that also, so we can't kill it with a kill command either. But you can always do kill-9. Kill-9 is untrappable. Alright, so any process you got, if you send it a kill signal 9, it'll kill it. If it doesn't, then you got something weird going on. So all these things, when you hit Control Z to throw something in the background, that's sending a signal, and you can trap that. So you can do different interactions.
Is there any way to create something that's like not even hard killable? Just
Not easily, but you can make poison pills. And that's always fun. Wall Street poison pill is like usually a stock option of some type that's so unpalatable that nobody would ever exercise it because it would basically kill the whole company. It's a way to get out of certain kinds of agreements. So in an operating system context, what would a poison pill be? A process that shares some resources with a very critical system process. And if you kill this process, the system will release those resources, and it will thereby release the resources that the system process needs, and everything will die after a few seconds. So you make a process that you could kill, but nobody would want to because it would destroy the whole system. So that's a fun thing to mess with. So when I was in undergrad, some friends and I were trying to figure all this stuff out. Somehow we convinced the administration to let us have unfettered access to the campus-wide computer system Saturday nights between like, I think it was like midnight and 5 a.m. And we could like close down the phone lines and let people come in, and we could do whatever we wanted to the machine. So we would play with all these kinds of things because we didn't have PCs and stuff at the time. But you can learn a lot by messing around with this kind of stuff, right? Figuring out like how operating systems do their things or how processes come and go, stuff like that. I might have told you this. My friend wanted to like change a process state without using the usual things like Control Z and BG. He just wanted to manipulate the internal structures in the memory and see if he could move a process from running to sleeping, which he was able to. And while he was doing that, I decided it would be cool to make time go backwards. So I found a spot in the operating system where every time that some event occurred, it would add 1 to a counter, and after the counter hit 10,000, it would add 1 to the number of seconds in the clock, and after 60, it would bump the minutes, and so on. And I just changed one little increment to a decrement, right? It was 2 bits I changed in an opcode, so that basically time would start going backwards. So I wanted to see what would happen.
Uh-oh.
Yeah, so worked great for a few seconds. I was in VI and I typed a right parentheses somewhere. When you type a right paren, if you have match on, it'll go back and show you the left parentheses for a few seconds and then come back. Well, it went over and showed me the left parentheses and it never came back because time never moved forward. Time was going backwards, so my VI session was hung. So I went over to another window and I started something else, and eventually after about a minute, everything just kind of like crumbled down and the system crashed. But it was a very slow and kind of glorious breakdown to watch as systems just started to fail.
So a lot of things relied on time.
A lot of things relied on time, and a lot of things not only didn't work, but did really bad things if time ran in the wrong direction, which was interesting. It's something that like I'd never like encountered before. And you know, no harm done. Nobody was on the system except us, and this is what we were trying to do, was learn about stuff. But yeah, so you can have a lot of fun tinkering with this stuff. And you know, if you've got a Linux machine or you've got Cygwin or something like that, you've got access to all of this. You don't need to talk to administration and get special permission anymore. And you don't have to worry if you break something, because if you're in a virtual box, you just reinstall, you know. It's not as precious, so you can have a lot of fun with this. All right, so let me show you the kill function. So we're still catching sig user 1. All right, so we got our ping pong. So the other piece of this is the kill function, right? So here's a main program. It takes one command line argument, which I assume is an integer. So I scan it into PID, and then I just go through a loop 5 times. I send a kill signal of sig user 1 to whatever that process ID is. I sleep 5 seconds, and then I send a sig term. And so this is going to do the same thing as when we use the kill command from the command line, except it's doing it from a C program. So I can do signal 2 and I can put in the process ID. So it sends a ping and a pong, and it's waiting 5 seconds, and it'll send another sig user 1. It'll send the third one, and a fourth one, and finally a fifth one, and then after 5 seconds it'll send a sig term signal. And I got my signal 15, but of course we're trapping that now, so it didn't actually terminate. But kill 9 will kill it. I don't know what signal 9 is. Oh, sig kill 1. Yeah, we looked at that. Sig kill. All right, so that makes sense. So that's just something useful when you start doing multi-threaded programming.
Can you trap any one of those signals out there?
You can trap any of them except sig kill. I think all the others are trappable. I don't know that for sure. And if you kill -1, it kills every process. Except the kill process itself and init.
Does hang through bash?
Either what?
Does...
Oh yeah, that's everything. That's basically like taking down the system, except for init, which creates everything.
That's like if you don't know what process is causing it, you just kill everything.
Oh no, I wouldn't do that. Because most of these processes, right? So right now we've got 240 processes running on my laptop, right? So yeah, I could take them all out with a kill of -1. I've never tried that. I'm not going to.
I don't think you should.
I don't think I should either.
That's exactly why we should.
Yeah, I would do it. I would do it in the virtual box. So kill 9, kill all processes you can kill. Kill -L translates.
Well, so kill all processes you can kill.
Yeah, so, but it's my laptop, so it'll probably let me kill everything. Yeah. But you could try it on a Linux server. There's the pretty table. I don't know which ones are trappable. You can Google that.
Or just try them.
Or just try them, yeah. So sig hup is the hang up, right? Back when you actually called up a computer with a telephone, and you would put the phone cradle into an acoustic coupler, and it would send beeping sounds across. And when you wanted to terminate that conversation, you would like take the phone and hang it up, and it like physically disconnects the audio pathway, so you can do the equivalent by sending a sig hup. Interrupt, quit, terminate, different versions of Control Z, and so on and so forth. Sig alarm is presumably used for expiration of some kind of timer. There was one I wanted to comment on. Sig power might be intended for like when there's a power issue. So your power starts going down, you send a sig power, and it's a high priority interrupt usually. It says, okay, we've only got a few milliseconds before everything goes away, so what's most important to us to do? And it's probably like saving the contents of memory somewhere or doing some kind of orderly shutdown. But that can be useful. There was one other I wanted to mention. Sig FPE, I think, is probably a floating point error, but I could be wrong. But these are used by different parts of the operating system, right? When you're doing arithmetic and you try to divide by 0, right? You're doing a divide instruction. How is that handled? I mean, every time you call divide, you could check to see if the divisor is 0 and do something special, but we don't usually do that. We just happily say, you know, something like this. Yeah, that's okay. Compiler shouldn't be that smart. So you run this and you get this floating point exception, right? Core dumped. I didn't put anything in here to say if the denominator is 0, then print out, you know, floating point exception. And if you look at the assembly language code, there's no equivalent to that. This is handled through basically an interrupt. When the floating point unit is called, and it's not really floating point, but it's still a floating point unit, and it tries to do a division, the state machine that's in there sees a 0 in the denominator, and it says, oh, there's a problem here. It sends a signal, and it's this probably the SIG FPE, floating point exception. And this is how the process responds to that signal. And you can trap it so that if you accidentally divide by 0 instead of ending your program, it'll print out some message like, hey, you divided by 0. That's okay, we still love you, and it'll keep running. Right, so this is also where operating system, hardware, user program, they all kind of come together, right? They're not totally independent of each other. Your program's running inside an operating system on top of hardware, and there's interactions between those. And this is a little bit of where that level comes into play. Same thing with arrays going out of bounds and so on and so forth. All right, so tomorrow I want to go through a little bit of a preview for 222. I want to do a refresher on structures and talk a little bit about pointers. Nothing that's going to be on the exam, okay? So you're done with material for the exam. But I want to touch on pointers and memory addresses and structures and passing structures and looking at them in GDB and just kind of play around with that for a day as kind of a prelude to 222 in winter. And then Thursday and Friday I'm going to leave for review basically. So there's a study guide already up on Canvas, but I'll leave 2 days for questions / review. So we'll start with that tomorrow.
So, what day was final?
What day is the final? It's either Monday or Wednesday, depending on which section you go to, but the schedule's on Canvas. And it's also on Clark's website.